Hello, my name is Doyun Choi and I'm a master's candidate student in KIST-EE. My teammate Hojun Lee is the PhD candidate student in the same major. From now on, we'll begin the review of the two papers. We have prepared papers on two topics, fairness and convex optimization. First, I will talk about the paper on fairness. The paper I prepared is titled Certification of Distributional Fairness and was presented at the 2024 NeurIPS conference. First, I will explain the background knowledge and the defined problem necessary to understand the paper. And then I will continue to talk about the running method proposed as a solution in the paper. Following that, I will show the result verified through experiments and conclude with a discussion. Before understanding the paper, we need to first understand individual fairness. Enforcing individual fairness in a model means ensuring that a given AI model outputs similar prediction results for similar individual data samples. Individual fairness can be categorized into three types: local, distributional, and global. A model is defined to have local individual fairness if it outputs differences within epsilon for all samples within the fair distance delta defined for a specific data sample. If a model satisfies local individual fairness for all data within the distribution, it is defined as having global individual fairness. As it has been demonstrated that machine learning models produce biased outputs for certain individual data, there have been difficulties in utilizing them in fairness-sensitive domains. To address this issue, interested in algorithmic fairness metrics that quantify the degree of bias in models has increased. Initially, heuristic approaches were used to debias models to meet fairness metrics, but this did not guarantee the fairness of machine learning models, thus failing to justify their application in fairness-sensitive domains. This eventually led to the emergence of certification approaches that provide firmer guarantees for meeting fairness metrics. However, when certifying the individual fairness on neural networks, if the number of neurons in the neural network exceeds a certain threshold, a new problem called the scalability issue arises. The paper identifies the causes of this issue as the enforcement of fairness for outlier data during the process of certifying the global individual fairness of neural networks and the computationally prohibited nature of the optimization process as the dimensionality of the input data increases. The paper aims to address these issues that arise during the process of certifying the global individual fairness of the model by replacing it with certifying distributional individual fairness. Distributional individual fairness is a type of fairness that is established when the average maximum prediction discrepancy is within epsilon for the empirical distribution and distributions with a certain Wasserstein distance. Now let's take a look at the method presented in the paper. The paper proposes a method to certify the distribution of individual fairness of neural networks to address the previously defined problems. The method attempts to solve the following two computational challenges. To certify the distribution of individual fairness of neural networks, the objective is to optimize the following objective function to minimize the upper bounds so that the average maximum discrepancy of the distribution within the Wasserstein bars within the given epsilon. I will introduce some mathematical approximations and tricks to overcome the computational problems that arise in this process. The method starts with the overall approximation of local individual fairness. Before this paper, when enforcing local individual fairness in a model, linear bounding techniques as part of MIRPA formulation was used to certify specifications within a specific fair distance. However, this method is computationally expensive for large neural networks. To reduce this time complexity, the paper applies this on axis-aligned isotope over approximations to the existing fair distance wall. This is to apply the formula for output bounds defined it in previous papers. By using this over approximate bound, the maximum bounds of the neural network output can be determined, and if this value is less than or equal to epsilon, the neural network satisfies local individual fairness for the given linear bound. The bound obtained in this process is used as the over approximation value for the previously defined maximum prediction discrepancy discrepancy function. With this newly defined local individual fairness, we move on to distributional individual fairness. To certify distributional individual fairness, calculating the Wasserstein's distance is necessary to determine the range of distributions to apply. However, it is impossible to define the Wasserstein bar for the empirical data distribution because we cannot access the empirical data distribution, and even if we know the distribution, calculating the distance is non-trivial. Therefore, this paper assumes a uniform PMF distribution for the n observed individuals using techniques from previous papers. This assumption allows to redefine the formula we need to calculate for distributional individual fairness along with the following constraints. Chernoff's inequality can be used to bound the difference between the final calculated value and the true value. To demonstrate distributional individual fairness, it is necessary to find the optimal pi that maximize the redefined formula, which give us the epsilon star value. However, finding such an optimal pi is a non-convex optimization problem, making it nearly impossible to find the optimal value. To overcome this limitation, the paper proposes to solving the non-convex optimization problem by instead finding the lower and upper bounds of the epsilon star value. The approximation value of the prediction discrepancy function for the following local individual sample is used to calculate this bound. We can find the lower bound of epsilon star through the approximated maximum discrepancy function using the PGD method, a type of adversarial attack. This approximate function is differentiable with respect to pi, allowing us to find the optimal pi using gradient ascent. By applying the pi obtained through the projection process to meet the previously defined condition, we can calculate the lower bound of epsilon star. To find the upper bound of epsilon star, we perform over approximation once again. Instead of altering the input distribution through distributional shift, we over approximate by changing the delta value of specific inputs. Using the probe provided in the paper, we can verify that applying the optimal Kusai value to the following equation results in the upper bound of the original distribution individual fairness violation. The upper bound can be determined through quasi-optimization utilizing the quasi-convex and Hölder continuous properties. The fairness of the model is granted by adding the previously obtained approximations of the certified upper bound of local individual fairness and the upper and lower bounds of certified distribution individual fairness as regularizer terms to the original optimizing objective and the performing optimization together. I compared and verified the fairness performance of the model trained with the three new optimizing objectives proposed in this paper against two baseline models. I used the income, employment, and coverage data from the PERC table dataset and evaluated the performance based on the following four metrics. The UCI data used in the paper was not provided, so only experiments that can be confirmed with the PERC tables database are conducted. As confirmed through the experiment, the accuracy decreased to the regularizer term, just as in the actual paper's result. However, for the four metrics directly related to fairness, all three objectives show improved performance, particularly for the two metrics related to distributional fairness. Optimizing the lower and upper bounds of distribution fairness result in much higher performance. I was able to evaluate the DIF bound on the distributional shift using the PERC table dataset. The model was trained on the California data from the PERC table dataset, and the estimated gamma from the paper was used directly in the bound calculation based on the Wasserstein distance distribution between the California data and each state's data. Based on the estimated gamma, the upper and lower bound of epsilon star was calculated, and the bounds were compared with the average individual fairness of each state through plotting. It was confirmed that for all three models, the lower and upper bounds effectively bounded the worst values of the average individual fairness on each state. In particular, the model utilizing the upper and lower bounds as regularizers showed a tight bounding. This experiment demonstrates that the validation of our upper and lower bounds against real-world DIF violations highlights the value of our bounds as a scalable, practical, and sound source of guarantees for individual fairness. This paper is significant as it proposes the first optimization approach and calculation for certifying the distribution and individual fairness of neural networks. In particular, this paper proves a convex relaxation of local individual fairness, enabling exponentially more efficient local IF certification compared with prior mixed integer linear programming approaches.
Hello, I'm Hojun Lee, and I'll give you a presentation about this paper, Online Convex Optimization with Hard Constraints Towards the Best of Two Worlds and Beyond. First, I'll tell you some backgrounds about online convex optimization, and then I'll define the problem that the paper tries to solve. Then I'll introduce the algorithm RecOO that solves the problem and explain some intuitions about the algorithm and asymptotic performance of the algorithm. Finally, I'll show the simulation result while I reproduce it. Many real-world problems requires us to continuously adapt to new information rather than simply concluding after one round of learning. Therefore, we consider online learning where we receive feedback from the environment over multiple rounds. An example of online learning is the online advertisement system, where we decide whether to show ad A to user based on their search history Q. Predicting the probability of user clicking on ad A is crucial, since the advertiser earns money when user clicks the ad. After the advertising system shows ads, the prediction model suffers logistics loss based on whether the user clicks the ad, which helps us improve the advertisement system through iterative refinement. Online learning can efficiently adapt under certain constraints, such as having a convex decision set and convex loss function. This scenario is known as online convex optimization. To formulate this, let large X be the decision set, assumed to be convex, and for T rounds, the learner chooses a decision and receives convex loss from the environment. And the goal is to minimize the total loss over T rounds based on past losses. To solve a real-world problem, one might consider the online convex optimization problem. But in actual situations, decisions may be subjected to constraints. For instance, in an advertisement system, the weekly budget constraint might limit the number of ads to be displayed, or certain ads might be restricted due to their appropriate for users. Therefore, let's consider constraint online convex optimization, which incorporates constraints into online convex optimization. This constraint may be known to the learner before making decisions or not. The goal is to minimize total loss or regret while also reducing constraint violations. Constraint violation can be defined in two ways: soft constraints and hard constraints. Soft constraints involve minimizing the sum of the constraint violation over T rounds. Even if a constraint violation occurs in one round, it can be compensated for in subsequent rounds by achieving GT be large negative. Hard constraint focus on minimizing the sum of rectified constraint violation over T rounds. Once a constraint violation occurs in a round, it cannot be compensated for in future rounds. COCO hard refers to constraint online convex optimization with hard constraints. The objective in COCO hard is to reduce hard constraint violation while minimizing total loss. Since achieving a total loss of 0 is often impossible, we compare a relative performance against a baseline, which is called a regret. One frequently used baseline in COCO is the static baseline. In the static baseline, performance is compared against the optimal solution of offline COCO, representing the best scenario where both loss and constraint function are known beforehand. The difference in performance compared to the static baseline is termed regret, and the goal is typically to minimize regret. Another baseline is the dynamic baseline, where the baseline can vary from round to round instead of being fixed at X star. The amount of the baseline varies is usually limited and denoted as PT. In this paper, the author proposed an algorithm named Rectified Online Optimization Algorithm, REC-OO in short, to solve the hard COCO problem. Let me explain the intuition behind this algorithm. The purpose of rectified decisions is to minimize the Lagrange function of the offline COCO. At the Tth step, we minimize LT. They approximated FT with FT minus 1, since FT is unknown in round T. To make the objective function to be convex, we approximated it with a first order approximation. Although FT and FT minus 1 are unrelated, approximating FT with FT minus 1 seems unreasonable. However, XT actually minimizes LT minus 1, and the alpha term makes XT and XT plus 1 closure, mitigating this issue to some extent. They approximated lambda t to QT minus 1 and rectified GT. After observing the constraint function GT, we increase QT by the violation in round T, setting the minimum violation to eta T. In this paper, there are 3 assumptions. Firstly, the feasible set large X is assumed to be convex and bounded. Additionally, both the loss function and the constraint functions are assumed to be convex and Lipschitz continuous. Without these assumptions, conducting online optimization would be impossible. We can divide the situation into 2 cases. One is the fixed constraint case, where the constraint does not change with each round. The other one is the adversarial constraint case, where the constraint can be set arbitrarily, which means it can be set adversely in each round. First, in the case of a static baseline, by setting alpha, eta, and gamma appropriately, we can achieve a regret of O square root t for both fixed and adversarial cases, and the violation can be made O1 in the fixed case and O t to the 3 over 4 in the adversarial case. case. If we add the assumption that the loss function is strongly convex, we can get better performance. We can achieve a regret of O log t for both cases, and the violation is constant for fixed case, and O square root t log t for adversarial case. For the dynamic baseline case, violation is the same as the static baseline case, and dynamic regret becomes OPT square root t. This table compares REC-OO algorithm and the best known algorithms. For fixed constraint case, the regret scales as the same as the other algorithms, but the violation is improved. For adversarial constraint case, the regret and violation is the same as the other algorithm, but is improved when we assume strongly convexity. The other novelty of the REC-O algorithm is that unlike the other algorithms, REC-O covers both fixed and adversarial cases with best known or better performance. And it is meaningful that there was no algorithm for dynamic regret and adversarial constraint case before, but REC-O can do. This is the simulation of REC-O algorithm. The paper simulated Cocoa Heart problem with some toy models, and I slightly changed the toy model and ran the code. For fixed constraint case, you can see that the cumulated loss is similar to other algorithms. And algorithm 1 in reference 35 has lower loss, but it violates the constraint a lot. For adversarial constraint case, you can see that cumulative loss is similar to other algorithm, and constraint violation is much better. Thank you for listening our presentation.